Hello students, in the previous lectures we have defined normal subgroup and proved some theorem based on the normal subgroup. Subgroup to be normal subgroup. Now in this lecture we'll solve some problem based on normal subgroup. Show that every subgroup of an abelian group is normal. Show that every subgroup of an abelian group is normal. Solution is what is given? Given is G is an abelian group, and let us go that H is a subgroup. That G is an abelian group, and H is a subgroup of G. Now our aim is to show H is a normal subgroup of G. So let us take for all X belongs to G and H belongs to H. We have X H X inverse. What do we have to show? Show that X H inverse X belongs to H. For H to be normal, because H is a subgroup. The subgroup means it is non-empty and it shifted all the fields under the coefficient, whatever coefficient is hyperbola. Multiplication in this case. So for all X belongs to G and H belongs to H, we have X H X inverse is equal to X X inverse H. If H is a subgroup of G, then it's a subset of G. So H and X both belongs to G. The group belongs to G. So and X belongs to G is a group. Therefore, X also belongs to G. So G is a average group. Therefore, for all X and X belong to G, X H H X inverse is equal to X inverse H. Here for G again. So X H to the whole unit. So X inverse X H inverse is equal to X inverse H. For G again. Now a Shetiko X inverse into H, you can add this as well. But X and X inverse is equal to E because G is a group, G is a big group, and E is added into this group. So X inverse comes out to be E. So E into H, and the tail of the group and subgroup is same. E into H is equal to H, which is the element of H. So this implies X H inverse belongs to X H X inverse belongs to H. For all X belongs to G and X belongs to H, implies H is a normal subgroup of G. The next problem is show that the set H consisting of second order matrices whose elements are real numbers A, B, C, D such that their determinant is equivalent of this second order matrix is equal to 1. Is a normal subgroup of a group G of second order matrices whose elements are real number and determinant is not equal to 0. So that this is a normal subgroup. Now what we have to show? Given is G is a second order matrix whose elements are real numbers and all the second order matrices of G is not equal to 0. And H is the second order matrix set of second order matrices whose elements are real number and determinant of whose elements is equal to 1. So this is it. Obviously, this is a subset of G. Now, in order to prove that H is a normal subgroup G, we have to prove that H is a non-empty. In order to prove any subset to be a subgroup, you have to prove that to be a normal subgroup, you have to prove that subset to be a non-empty. That is subgroup. That subset is subgroup, and then it will become a normal. So it will happen. So first is since this is identity element, is equal to I is equal to 1, 0, 0, 1, whose determinant is equal to 1. So therefore, this I identity matrix of second order of H. So therefore, H is a non-empty subset of G. H becomes non-empty. Second is we will show H is a subgroup. Let us take two elements A consists of A1, B1, C1, D1. ABCD, A1, B1, real numbers and determinant. And B consisting of A2, B2, C, B2, which are real numbers and determinant equal to. Now, determinant of A into B, we know that determinant of product is product determinant. Determinant of A is 1, determinant of B is 1. So, A into B determinant is equal to comes out to 1. This implies A belongs to H. Similarly, determinant of A is equal to 1, which is not equal to 0. So, A is notable. If A is notable, the inverse of A is written adjoint of A1. Now, here, determinant of inverse will be equal to determinant of adjoint of A upon determinant of. Now, if A is the nth order matrix, then we know that A nth of square matrix, then A to adjoint of A is equal to adjoint of A is equal to determinant equal to I. So determinant of the, if we take both sides, determinant of A to adjoint of A becomes determinant of A into I, or and if you split that, determinant of the product this matrix, then the matrix is different from A by this element by their cofactor, then that translate that. So product is determinant, property determinant, and determinant is equal to, if you multiply each entry of, if you multiply, it is a real number. Real number, if you multiply nth order matrix by A and mind do that, this comes out to be determinant by n. Determinant of adjoint comes out to be serial number. So in draw, where it is. So A is the second order and comes out. So here, this is the matrix of second order. Determinant of adjoint of A comes out to be 2 minus 1. Determinant A upon, and determinant this will be how much? You have to apply each multiple matrix by some number. You have to multiply each entry by that. So this comes out to be determinant of A, determinant of A upon A in this case. So now determinant will cancel. This 1 upon determinant of A is equal to 1 upon determinant is equal to 1, 1. So determinant of inverse is equal to 1 implies A inverse of the. And lemma implies closure property holds true and inverse matrix. This implies this H is a subgroup of. Now this for eligible to H, A to be eligible to H, and eligible to H, lemma implies H is a subgroup. Now I need to show that this H is a normal subgroup. For normal subgroup, let A belongs to H and B belongs to G. Any inverse. So if A belongs to H, determinant is equal to 1. If B belongs to G, determinant is not equal to 0. And if B is not equal to 0, B inverse is equal to B inverse exists. So inverse exists, then therefore B into B inverse is equal to I, and B determinant of the product will take them both sides. Determinant of identity matrix is equal to 1. Product is product determinants of determinant of B inverse is equal to 1 upon 20. Now I will show that B inverse belongs to H. So now B inverse determinant, first we show this is equal to 1, and then if this is equal to 1, they belong to H. So determinant of B inverse is equal to the product. B determinant of B inverse is equal to 1 upon B cancel. Determinant of A is equal to I, so B is equal to 1. This implies B inverse belongs to H for all A belongs to H and B belongs to G. Hence, Hj normal subgroup. The next problem is prove that the center of the group G, the center of group G of the group G is a normal subgroup. And center of group, we know that center of group is the set of all G belongs to G such that Gx is equal to Xg for all x. So what this? So now this implies the center of group is a subset of this set of center of groups is a subset of G. Now our aim is to show that the subset of G. So we have to again show this center of group G is known as A. This is a subgroup and the normal subgroup because we want to show that this is normal subgroup. So this we have shown this subset. Now after subset we have to show that it is known as A. Then we have to show the subgroup and we have to show That means this is a normal subgroup. Since E into X is equal to X into E for all X belongs to G, if it is into X is equal to X is equal to E is equal to X for all X belongs to G, so E this implies E comes to ZG. So therefore ZG is a non-empty subset of G. Now second look, this is a subgroup. So for all AB belongs to ZG, we have any two elements, then if they belong to G, then A into X is equal to X into A and B into X is equal to X into B for all X belongs to G is a group and the cancellation of objects. So if we apply the right cancellation law by B inverse, B inverse comes out to E, left cancellation law by B inverse, then this will become B inverse into B is equal to E. So this becomes B x B inverse is equal to, if Bx is equal to xb implies x B inverse is equal to B inverse x because G is a group and H is a group of H subset of and G, ZG is subset of. So what is implied? Now I want to show that ZG is a subgroup. For subgroup, we will show that now we have given X A B inverse lemma. We are applying lemma to show this. X A B inverse is equal to a shift hold because X and A and B are belong to G and the shift hold in G. So this is equal to X A B inverse is equal to a shift law X A into B inverse. X A is equal to how much? Because A belongs to G. A belongs to ZG and X belongs to G. Therefore, X is equal to AX into B inverse. Again, I should know. So X A X B inverse belongs to G. B inverse also belongs to G. X B inverse is equal to B inverse X. So using here is equal to A B inverse X and I should below this is A B inverse X. X into A B inverse is equal to A B inverse X implies therefore A B inverse belongs to ZG for all A B belongs to ZG. So to show that that is a normal is a sorry subgroup of G using the network law. Now I will show that ZG is normal. For Z is normal, let H belongs to ZG and G belongs to G. If H belongs to ZG and G belongs to G, then GH is equal to HG. H is equal to HG because this is a ZG is a subgroup. So now I will fix normal. This is a G and G inverse. So G and G inverse to ZG. G and G we are taking the element. G and G inverse is equal to GH initiative law belong to G. GH is equal to GH into H. G inverse is equal to GH is equal to HG. G inverse so this is equal to I should again G G G H G G inverse is equal to E. So H into E is equal to H belong to H was the element of H. So this implies G H G inverse is equal to H which belongs to ZG implies G H G belongs to ZG for all X belongs to G and X belongs to ZG and this is normal. ZG is normal. Next problem. If H is a subgroup of G of index 2, so means number of right or distinct left or right opposites of H in G are 2, then H is a normal subgroup. If H subgroup G, an index of index is 2 in G, of index 2 in G, then H is a normal subgroup. Given is H is subgroup G, such that then distinct right and left position of H in G are 2. H is equal to therefore number of distinct right or left positions. To prove is what to prove H to that H is normal. What to prove? To prove that for Hx is equal to Xx is equal to Hx for all x equal to G. That is not normal. So that is solution. That quotient is equal to and subgroup subset of G, subgroup of G. Because subgroup will be a normal subgroup, the left quotient of H in G is equal to right quotient. So let X belongs to G be any arbitrary element. What to show? To show that if X is any element in G, then two possibilities can arise: X m belongs to H or X can't belongs to H. X belongs to the next one. So if X belongs to H, X is also element of H. Then since X belongs to H, so X into H is equal to X is equal to H into X. X into H is equal to, because H is a full property whole true. Therefore, this implies X is equal to X. True for H. But if X does not belong to H, then Hx is not equal to H, and X Hx Xx is not equal to H, and Hx is not left cosec of H is not equal to H, the subgroup itself, and right cosec is not equal to H. And also the index of H in G2. So if index of H is 2, this implies H in G have two distinct left or right process. This implies H in G have two distinct right or left process. So that this implies G is the union of these two left right process is the union of H union XH is equal to H union left process into H is equal to H left process H union XX is equal to G is equal to H union HX. Now if H union HX H union XX is equal to H union HX implies they're equal, so H is equal to H, so this implies XH must be equal to H is equal to HX. So A implies H is the normal subgroup of G, whether you X belongs to H or X does not belong to H. Now next one. Now prove that a subgroup H of a group G is normal, then HA into HB is equal to H of AB for all A belongs to H. Okay, prove that a subgroup. Let H is a subgroup G, and this normal. Let H is a normal subgroup G. And let us take HA and HB are two right cosets of H in G. Then HA into HB, HA into HB is equal to H of A H into B, H of A H into B, because H is not also good. So H A is equal to H A, A H is equal to H B. So this become H of A H is equal to H A become. This will A H A B is equal to H A H B. So this H is equal to A H. That is the right question because it's normal. H is equal to A H. So this will this substituting value now H A B. This can be also written as H into H of A B. H is subgroup H into H is equal to H. It's going to be written as H into H into H of AB. H AB. Now what is this? A and B belong to G. G is a group, so A also belongs to G. So this implies HAB is the right cosec of H in G. G implies if proved every subgroup of the normal, then the product of right is the right.